So my talk today, actually a title at first is that's a rule of randomized control trial apply for big data, and I changed a little bit. Can big data replace randomized control trial? And so my outline say I'm going to talk about philosophy of science and RCT, and then logic of causal inference and fallacy when we make causal inference. Because in medicine, we always want to make a causal inference. What is exposure and outcome? And then I talk about big data and its characteristic, especially a big data in medical science, and how can big data facilitate causal inference, which actually very, very repetitive to what Caroline and what other speaker already talked about. It. So I say, yes, that's a rule of RCT still apply. And can big data truly replace RCT for efficacy research? Obviously, maybe not, yeah. So, yeah, when we start in the medicine, we talk, the first one who really implement experiment may be Ignaz Semmelweis in Vienna about 1818, about perpetual childbed fever, where he tried to watch chlorine hand wash before a normal labor and result in a lower mortality of childbed fever in a Vienna hospital. That is the first experiment, and he even don't know what is germ, what is bacteria of that cause childbed fever. And this case study become a very classic case study in any textbook on philosophy of science and experiment. Unluckily, he died very young. And then Louis Pasteur know the process of pasteurization, where he has a bowl flask shift and see when we can pasteurize and protect food from being rotten and so on. And again, Joseph Lister in London spray phenol over the patients while operation and see the effects that result in lower mortality. This is not truly randomized controlled trial, but a kind of manipulation to see how they can prevent germ and bacteria in a medicine. Randomized controlled trial actually result from this guy, Ronald A. Fisher, who invent analysis of variance. These two books, The Design of Experiment, truly discuss about randomized controlled trial, where you need a control group and experimental group, and that's have a heavy influence in RCT from that time. Now, what actually a logic of causal inference and fallacies when we make causal inference? We go back to John Stuart Mill. He say that causal relationship exists with three conditions. First, the cause preceded the effect, which temporal sequence, if X, then Y. X must happen before Y. That's why we need manipulation in experiment. And then the cause was related to the effect. This is necessary but insufficient condition, as we know that correlational sequence or correlation doesn't imply causation. And we see a lot of weird things, say that people who born on Libra or Sagittarius have more exposure or risk of myocardial infarction, which is not likely to be true. And also, John Stuart Mill say that we can find no plausible alternative explanation for the effect other than the cause, which is in economics we call et cetera publis, every other thing being equal or whole constant. And I would like to add, causation needs theoretical explanation or theoretical sequence, which is a must. Otherwise, you have to be very meticulously when we infer something about cause and effect. An experiment can establish causal relationship and causation because in experiment you manipulate something and see what will be next. So you include temporal sequence. You can investigate the cause and effect through correlational sequence. And again, with a meticulously design, you can control any extraneous or confounder. So this is like a very common RCTs. This is from a consort, which all people in biostats and epidemiology really know that you need eligibility, and then you randomize people into two groups. One always intervention, which is a standard intervention or standard treatment, and you have a new treatment, and you receive intervention, and then you have a follow-up, and you analyze data. So randomized plays three things. First, eliminate selection bias. The control and experiment group must be exactly the same, no selection bias. And also want to eliminate confounders, because randomization, if randomization really works, and if you have a very well-planned experimental design, like you try to develop a new drugs for HIV, for example, you can also increase sample size to achieve statistical power with a well-planned design. Actually, RCT is actually randomized pretest post-test control group design, where experiment group you have randomization, you have observation 1, and then you have treatment, and then observation 2, and then for a control group you have randomization, observation 3, and observation 4. But purely control group can be considered unethical in medical science. So people in medical science always use standard or standard treatment as a control group. And then if randomization work, O1 must be equal to O3. And if there's no other threat or history or maturity during the experiment, then O3 must be equal to O4, no threats to internal validity. Well, we are really, really concerned about the third one, which is a confounder. And there are 4 main strategies for controlling extraneous variable in X design, including randomized control trial. The first one, of course, is randomization. We have randomized pretest post-test design, and matching, which you can use match pair design, you can use randomized block design, you have twin studies, especially like, monozygotic twins, which is rarely to be true, it's not practical. Also, a newer idea called propensity score matching, where you try to match between 2 groups and modes of treatments to have the same background or same other confounder. And the third one, you try to include confounder variables into experiment itself, like you design factorial design and so on and so forth. And the last one, we use a method called regression, which is actually regression. So the last question somebody just asked, which one you prefer between regression or matching or propensity score, actually is here, okay? Say you can control using covariates, where you collect data which is a confounders in your design. Some analysis say multivariate analysis of covariance, you use analysis of covariance, or other multivariate technique can be applied as statistical control. And this is our 4 main strategies for controlling confounders in your X design, so that you can make your causal inference firmly. Well, without randomization in medical science, can we really infer a causal inference? The first and the very classic one in medical science is a fluoridization and tap water, which and quasi-experiment, because you actually cannot do a randomization. And a dentist, I think in New York, I cannot, their name is here, Smith, Watch, Cantwell, all day. They choose 2 communities along Hudson River, and then that 2 communities are very similar in terms of socioeconomic status and geography and everything. And so they put some fluoride into tap water in one community, and the other one, they don't. And they found that a prevalence of tooth decay declined afterward without any randomization. One nice thing about quasi-experiment, it's more practical. When you can't do randomization, you still do experiment, but it's quasi-experiment. It's not true experiment like RCT. But if you carefully select the site and make your outcome comparable, because they have all other background and confounder quite very similar, then you can still make a causal inference. this is not purely experiment and not purely observational studies. And people still, in medicine, still make a causal inference. Okay. Yeah, there's a lot more on quasi-experimental design that make you able to make a causal inference, like interrupted time series design, or comparison time series design, or regression discontinuity design, where you have a pre-test and post-test, and you use a pre-test as a cutoff, and then you implement, you assign a treatment for those who have a pre-test score cutoff more than something and something. And thus, you will see regression discontinuity between test, pre-test, and post-test. This is a very famous one, quasi-experimental design for program project evaluation that has been used widely in health science and in education as well. So what is the fallacies of causal inference? This is an Ig Nobel Prize in neuroscience, the dead salmon brain, where they bring the salmon from Atlantic Ocean into MRI and see how their dead brain wave blink, and a lot of blink. But again, correlation does not mean causation, and all event-related procedure may be just a voodoo size if you don't make it carefully, because there's a lot of noise. That's why we need Fourier analysis and so on. And what is widely used? We use DNA and RNA sequencing, work by Frederick Sanger, Watson and Crick double helix. We actually do categorical data analysis of ATCG, and then we have a tag whether they have some kind of disease or not, and try to find a pattern out of it. Again, it is not experiment. It's just finding the different pattern between, say, people with diabetes or without diabetes. And this can be voodoo science as well, because it's actually correlational research, but not experimental research per se. Temporal sequence is extremely important. People are talking about fMRI, where you can see the change of your brain wave when you do some kind of activities. But again, we actually don't know, because the brain is very, very complex, and people may think or may have another various brain activity at the same time, and we even don't know. But the paper published using fMRI increased time by time very tremendously. Yeah, but a lot of spurious correlation is always there. Say a correlation between people who drown after falling out of fishing boat and marriage rate in Kentucky states. There's a lot more. Okay, and why big data come to play and make and facilitate? Actually, medical science may be a very, very first one who use a lot of big data, because in your medical record, a doctor gonna write something like an essay and also draw a picture of organ with a lesion. Sometimes they have MRI film and a lot of picture, voice, even voice, you use stethoscope and Internet of Things. And a characteristic of big data, the first one that people talk about it is volume, the size of data getting bigger and bigger. But that is not actually very important. In the old day, you don't have electronic medical record, but right now everything is on computer, and all patient records already there in computer, so make everything easier. A velocity, you already have a lot of sensor. We have a sensor that can detect patients' symptoms and say oxygen saturation and so on, which is a real time, and we have real-time data analytics and data streaming. And it's really, really fast, and how can we capture and analyze those data? And the most important things to me is variety of data. That is the most challenge for big data analysis. We have text in medicine where the doctor write a record. We have a picture, either MRI or a biopsy and so on. And we have voice. But the most important thing is veracity, trustworthiness of a data. Something like a lot of mistakes, especially typos and misclassification, or something is missing in a hospital medical record is something very, very common and always happen. How we can clean those data before the analysis will be implemented. That's most important thing. And yes, we want the right data to answer our questions. We need value. Otherwise, we will have something like vagueness, variability, That's not what we want, okay? And a big data come to play a role in medicine, like personalized medicine. We have one person tries, one single subject, which is a time series design. And you see how people change over time. That's one thing, okay? You use biosensor, you use Internet of Things to collect data, and you can see how treatment change people over time. We have more longitudinal data through a big data and biosensor and Internet of Things, and make your causal inference easier if you wisely use it and analyze it. Again, and some people, this is from plus one, people in medicine are really worried that they will no longer have a job or lose their job. For example, heart doctors say, oh, machine learning, and I already read this paper, they even don't use a complex machine learning. They use something very simple, but perform better than cardiologists. I swear, way better than cardiologists in diagnosis or predict the risk of heart failure. Computer beats doctors for sure. Oh, wow. And what's a doctor's new job then? Okay. So, yeah, there's a lot of information loop from big data that can be used in medicine. But how big data facilitate causal inference? Well, one thing, big data can bring you more longitudinal data because you have biosensor, you have Internet of Things. So you can include temporal sequence. Another thing, you have more variety of data where you collect more confounders and so on that can use to do something else. This is a very influential paper in JASA, Journal of American Statistical Association, written by Paul Holland. Two of them, Donald Rubin and Paul Holland, they worked together on statistical, on causal inference. And what the idea, because they used the idea of matching and covariate inclusion in the same paper. They use both regression method and matching here in order to control for confounder. And this is what they call Rubin causal model, which later on become propensity score matching. This is a theorist who invent a theory for propensity score matching. In several papers, they talk about estimating causal effect of treatments in randomized and non-randomized studies or observational studies. This is a work by Ron Rubins and propensity score. With big data, you have more variety of data, especially electronic medical record. You can use either, if you have a time series, you use previous outcome or previous exposure, any other thing that you have, you can use it to control or do propensity score matching. That make your causal inference firmer than before because you have more data. And it's even easier because everything is already on electronic files. Your job is to do extraction, loading, and transformation so that you can analyze it easier. Again, also big data also facilitates temporal sequence, which is a very important condition for causation, as John Stuart Mill has said. The idea is from Granger. Granger is actually economist. This is his influential paper in Econometrica in 1969, and he received a Nobel Prize in economics in 2003. He actually worked as economist, so he works a lot on time series data. And in fact, a lot of medical science right now with Internet of Things and biosensor, you already have longitudinal data or time series data. And he tried to see whether a time series of X1 and X2 and Y, is there any way that we can make causal inference that X cause Y through observational study? And this is what we call Granger causality test. I try not to be so too technical, but sorry. Is that, can I use equation just a little bit? This is a Nobel Prize. Okay. So say you can see a time series of X, say X is exposure and Y is outcome, okay? And you see a pattern are very similar except that there is a lag between X and Y. So that you use Granger causality test is actually regression method where you try condition predict Y at time t with a lag t minus 1 and yt minus 2, and again with xt minus p. The strength of Granger causality test, they try to include temporal sequence in a prediction, so make a causal inference firmer than before. And I'm pretty sure that Granger method can be used for big data in medical science, because now you have IoT, you have biosensors and a lot of electronic medical record. Okay, and another one which is not really a long lengthy time series, you have a panel data. Say I work with my students right now. We have a yearly physical checkup for normal people who visit a hospital once a year just to check their cholesterol, blood pressure, you know. So it's actually several waves of data, and we used like 3 or 4 waves to see which one be a cause. In this case, I choose one paper from Korea where either we want to answer whether nicotine dependence cause smoking or smoking cause nicotine dependence. So we have wave 1, they have wave 2, and they have wave 3, and they measure nicotine dependence from chemical substance or something in the blood, and they have average smoking in a 1 year. So this is year 1, and this is year 2, wave 2 data, and this is wave 3 data. This is what we call panel data. And you know, if you have physical checkup, you always have this. And if it's in your electronic medical record, then it's easier. We just use SQL to retrieve it and to analyze it. So this is X1, XT1, XT2, and then X33, and then YT1, YT2, and Y33. And what they use is actually they use the method called structural equation modeling to incorporate temporal sequence in causal inference. And one nice thing, you always know that the best predictor of the future is past behavior. Say nicotine dependence at time 1 can predict nicotine dependence at time 2, and nicotine dependence at time 2 can predict nicotine dependence at time 3. Again, average smoking at time 1 predict at time 2 and predict average smoking at time 3. This is what we call habituation. People always do what they have done in the past. Okay? But one nice thing, when you have a cross-lag here, we found that there's no very, very low correlation from average smoking at T1 to not nicotine dependence at T2. And again, average smoking at T2 have very low correlation with nicotine dependence at 3,1, which means we control for the path of both X and Y here, but we find 0.34 here, we find 0.34 here. So in this model, it's likely to be the case that nicotine dependence causes average smoking rather than vice versa, where average smoking causes nicotine dependence. This is clearly seen when you incorporate temporal sequence in your analysis of causal inference. And if you have very good electronic medical record, you have to do nothing, just ELT, extraction, loading, and transformation, and then analyze it, and you make firmer causation in causal inference. Can big data truly replace RCT for efficacy research? I would like to say no, no, and no, of course. But all the rule that applies in randomized controlled trials still apply in big data if you want to make a causal inference. Big data can facilitate causal inference for sure, because you can do matching easier, you can use statistical analysis to control for confounder easier, you can include temporal sequence where you have a previous outcome and previous exposure, previous risk factor in your analysis easier. But again, you know, randomized controlled trials still needed, but a lot of variation from one clinical trial to another clinical trial. You may see that, okay, some kind of, you know, medicine work for some people. One man's meat is one man's poison. And then we really need another kind of big data. Say we need to do meta-analysis and systematic review like Cochrane project, where you have very big data so that you make your causal inference even firmer. And again, one nice thing about meta-analysis and systematic review, you can find moderator, what really shifts the relationship between cause and effect. And that's how big data come to play in causal inference and randomized controlled trial. Okay, that's the end of my talk.